Oh, we're always ready.
Okay, so the first thing is if you want this presentation later or to refer to it, you can find it here at this web page.
Okay, you'll send it, we'll put it on our web page.
Yeah, I mean, or you can just link to it, whatever you prefer.
That's a condition for getting paid.
Yeah, that's easy. And then if you actually want to look at, well, I think all the R code's visible here, but if you want to look at the raw R markdown file thing that I used, that's on my GitHub, which will also be linked with the data lab wherever. Okay, so first, the structure of this talk. I'm going to first talk about sort of basic R optimization with the idea that you would then want to use some of these things to make the things that you run on HPC faster and more effective. Then I'm going to delve into some necessary UNIX or StarNix stuff, because the HPC is all on Linux. And so basically to do anything, you have to understand sort of basic Linux type stuff. I'm going to go through some of that, but I mean, you know, there are billions of tools on the internet to teach you more about this stuff. Then I'm going to talk about sort of the basics and the setup of HPC. Then I'll talk about specifics for NYU, and then examples. And I really only have one sort of extended example, which is doing cross-validation on a latent Dirichlet allocation model that I've been working with. Okay. Yes, and please interrupt at any point, because I just sort of like threw a bunch of stuff together that I thought would be relevant. So if you have specific questions about anything, I can go into more detail. Okay, so we're going to start with R optimization. I'm going to talk about basically two types of optimization, which are compilation and multiprocessing. Because there is no multi-threading in R. R runs as one program of R on one core at one time. You can get around this kind of, but essentially there is no multi-threading. Okay, so here's a sort of traveling example we're going to look at in terms of benchmarking some of this stuff. Yeah, so we're going to think about the following task. I'm not sure these numbers are right. We can look at the code in a second. But given a vector of 5,000 values, oh yeah, I changed something. So we're just going to take the mean of each group for 100 equally sized groups. And this is the code, so we just sort of generate some variables which have different means. Let's say we randomly order, we set up group labels, then we have these functions which are what we're going to repeat over and over to sort of get our benchmarks, which is just, we have one version which just uses a for loop to take the mean, the grouped mean, and then we have this using the tapply, which is sort of this helper vectorized function that R provides, which will take the group specific means. Okay, and then we have this function here, which is our function that will repeat something a bunch of times so that we can sort of get a more accurate feel for the speed of it. So what we do is we're just going to, by default, repeat something 100 times. We're going to take the time when we start. We're going to, if we want to compile it, I'll get into this later, but just for the sake of having a single function, we compile it first, and then we just repeat it this many times. Then we take the time at the end, and then we only return the average running time. So the first thing we do is we just repeat doing this for loop thing 100 times, and we take that time, and we do the same with the tapply. So then what we can do is we can look at the relative speed of these two methods. So the first thing we see is that using a for loop in R is slow, very slow. It's 3 times slower than using the tapply. And I'll talk a little bit about why that is in a second, in a little bit, but for now, this is sort of our first lesson, is that vectorizing your code is good. Vectorizing meaning you're sort of operating on the level of a vector rather than individual small operations. Okay, so now let's think about doing the first thing that we can do to speed it up, which is compiling. So remember over here, this little bit of code, if we wanted to compile, we compiled our function before we ran it. So, but I'll show that. So for a while now, I think since like 3.0, R has shipped with the compiler package pre-installed. So you shouldn't need to install it. You should just be able to load it in. And this allows us to sometimes speed things up depending on exactly what we're doing. Andrew, are you raising your hand? Okay, just playing around. Okay. So then the basic idea of compiling, for those of you who don't know, is that basically compiling is slow. It takes a while, but it makes that bit of code faster to run in the future by compiling it down to a lower level. And so running compiled code is fast. So these are in quotation marks because this is all very relative and hand-wavy, but in general, this is the idea. But here's the other interesting thing is that also for a while, R has started compiling a lot of the sort of basic tools that you use when you start up R. So like the mean function. So you know how if you just write the name of a function in R, you can see the code. So if you put in like mean or mean.default probably, whatever it is, for a lot of these basic functions, you'll see that it doesn't actually have the code for the function. It says like dot primitive or something like this. This is because it's compiled. Or at the end, it'll say like bytecode and then give you a little number. And it's because R compiles a lot of these functions by default, or just writes them in C++ or Fortran or whatever. Yeah.
If you compile a function in R, would it be as fast as if you wrote it in C?
No.
Okay. That would be nice.
Yeah, it would be, but it's not. Okay. I don't know if I have any examples about that. Not really. Well, actually, I kind of do, and I'll talk about that in a minute. So we can compile a function. So given that we've written some function to do something, we can just compile the function with this sort of compiler function, CMP fun. So that's what I was using in the previous thing. I accepted a function and I just compiled it. So now let's do our benchmarks using compiling and see what kind of speeds we get. So we actually see something interesting, which is that tapply and applying and compiling the tapply, actually compiled tapply is a little bit slower. So the reason why this is because tapply is one of these compiled functions. And actually, here's something that's ridiculous about R that I just learned, is that vectorized code in R is not truly vectorized in the sense of like that it sort of, uses multiple registers on the processor at once or something like that in a smart way. It doesn't do that. It doesn't do that kind of vectorization, which is what like a low-level programmer thinks of by vectorization. What it does is it compiles it basically by restricting the way you can write your code by using like a tapply or something like this. It can then compile to faster bytecode, non-vectorized bytecode. So that's sort of something weird that R does. John Miles White has a blog post about this that he put up like 2 months ago. That kind of weird. So anyway, and we can also see that we're not getting huge speed-ups with the for loop either. You can't even really say this is any faster because it's just sort of like some random variations in runtime. So what this did here is instead of actually compiling the function and including the time that it took to compile in the timing, I'm just compiling it before it gets to that point. And so it still doesn't take long to compile. It's just not a lot of time that this stuff takes. And so the reason for this is because, so I talked about it over here. So we don't get any huge speedups. When you will get speedups are when computational burdens are pretty heavy, rather than just sort of like basically subsetting things, which is the only thing that we're doing that wasn't compiled. So the mean function is already like pre-compiled. So we wouldn't get any speed up on that, we're only basically getting speed ups on the subsetting, if at all, and we're not really getting anything. So, but we do get huge improvements in vectorization, and that's because it can compile. That stuff is sort of by nature just running faster because of like the way it does things under the hood. So most common functions are already compiled in either like C++ or Fortran. So gains on really simple functions are going to be limited. So what you should think about is that compiling in R is generally going to sort of speed up all of the glue between the actual like primitive things you're doing. The primitive things are not going to get any faster, but all the glue between them, that's where things are going to get faster. So adding in heavier computations gives more of an advantage to compiled functions. So here what I'm doing is I'm just taking the same stuff that I've been working with, and I sort of like do some multiplication here, do some subtraction across vectors, then I calculate a cross product, which you would think would be pretty slow, and then I run a couple for loops here, also which we know should be pretty slow. So I'm doing like a lot of computation in here. And so then I run it once, where I just run through it uncompiled, and then I compile it. And we can see here that we are starting to get some significant speed increases. So this is when like compiling is generally going to help you. Okay. Then, so a nice thing that R does is what has become awfully trendy in the last couple years is just-in-time compiling. So what the hell is a JIT? I don't know. I don't know who decided to name it this, but it's just-in-time compiling. So what this means is it compiles the function just before you use it for the first time. It compiles it just in time, hence the name. And so what this means is that each subsequent, the first time you run the function, it's going to be a little slower because it has to compile it, but every time after that, it's going to be at the like compiled speed. So Chrome does this with JavaScript. This is one way that they've made their JavaScript faster. And they're doing all kinds of, they're actually changing this around, and they're doing sort of another different weird thing that's not quite just in time, but basically that's what they still do. So this is basically the same behavior that we forced in our retfun function, which was that the first time we wanted to execute it first, we compiled it. So that's, yeah. So you can tell R to automatically do this, and you do it by in your .r environ file, which is just sitting in your home directory, which is just normal home directory for Linux, Unix. I don't know what it is in Windows. It's probably like your My Documents folder or something. So you put in these two lines, which is R compile packages is to true. So this will, when you load a package, it's going to compile all the functions in the package. Then you can also enable the just-in-time compiler to 3 level. That's sort of like where they're compiling like everything, basically. And in my experience, I've had the JIT enabled for quite a while now, and I haven't noticed anything being like crazy slow. My feeling was, I don't know if it's a placebo effect, that it did like speed things up quite a bit, and it's just fairly simple to use, so I like it.
Just a quick question.
Yes.
So when you change a function, is it clever enough to know that you changed it? And you say it, and you don't have to keep it?
Well, I mean, so if you were going to change a function, you'd have to resave it back. You basically would be rewriting it and saving it back to a variable, right?
Right.
So yeah, it would have to recompile.
No, I know that.
It would do that.
Does it know enough to recompile?
Yeah, yeah.
I mean, because
It would.
the pain of compiling is always, until you've got something that's in production ready, you don't want to keep, sort of compiling.
Yeah, yeah. So it does. I don't know exactly how it like detects, but you will notice that it, like I said, when you just sort of like type out the name of a function in R to like look at the code, if it does compile it with like just in time or whatever, it'll say at the bottom like it's like a less than bytecode : like a hex code and close then yeah, greater than. So it does show up somehow. I don't know exactly the internals, but so it will know. Okay, so multiprocess R. So yeah, like I said earlier, R does not use multiple cores unless you make it, and even still, then it's not really. It's sort of creating multiple instances of R. It's not actually like just using multiple cores. A single R process can only use a single core. So what we have to do is we have to start up a bunch of R processes, and then we sort of let them talk to each other. And this is all automated for us. And the simplest way to do it, that at least in my opinion, is just straight up the SNO library. This stands for Simple Network of Workstations. So you hear this, and it's sort of funny. You're doing the equivalent of running a cluster on your machine, is what you're doing with SNO, which is why it's called Simple Network of Workstations, because it's like between workstations. It's the same thing. So here's the code to do this. So what you do, you just require SNO, and then you tell it to start up a cluster. And you tell it how many cores to use or how many machines to use. So then what you have to do is you have to write your code slightly differently. So here I'm using, so instead of like your apply family of functions, you use par, lapply. They have a bunch of them. They don't have tapply, which is why I just looked at the code of tapply. This is the same thing that tapply uses internally. So it's the same type of function. Yeah. So it's basically just a special version of the apply command function, which you tell it to use the cluster. So that's our do tapply with the cluster. We can also repeat a function using the cluster, which means that when we were doing the 100 iterations, we can split up those 100 iterations within our 4 cores. And so this is the way you would do that. So this is, again, the same internal way that replicate works. So I just ported out so it's sort of comparable. Okay, and then so we can just add into our benchmark these times. So I do a couple different ways, let's see. So at first I just I do the tapply using the cluster. So this is for every time, for every little tapply we're doing that on the cluster. But remember the tapply was pretty fast, so yeah. Then I also do the repetition, but this time instead of doing the clustering at the level of like sort of the primitive basic little task I'm doing, this time I do it within the 100 iterations. So I'm farming out the 100 iterations. And then the final thing is, so I do this same thing where I farm out the iterations, but I just do it with my basic for loop that I had before. So what we can look at here is we can see that in fact the clustering here gets a pretty significant speed up. So before our tapply was the fastest, now the tapply is about 2 times slower than farming it out to our 4 cores. So this, you may hear that and be a little surprised. Yes, we are farming it out to 4 cores, but we're only getting about a 2 times speed increase. And you should expect this because especially when things don't take very long, sort of just cumulatively like here, you're not going to see like a huge multiplicative increase in speed because it sort of has to, you can think of sort of scheduling out how it's dividing the task, and then it has to take all of the individual bits and join them back together again. So it's having to do some more things that it didn't have to do before. So let's see, what else can we compare? So there were some other things that I was going to talk about. So doing the clustering at the sort of basic level was actually a little slower than just running tapply. So this is something I've run into before, and it's because the individual task is just not sort of hard enough to justify farming it out to multiple cores. So this is you can't just sort of without thinking apply clustering and expect your speed to go up a lot. In fact, your speed might go down because you really have to be thinking a lot about whether the individual tasks you're doing do sort of like take a long time. Because if they don't, then there's not going to be much of a reason to farm it out. But let's see. So yeah, so let's see, which was so we got a pretty big increase on our for loop too. So before it was about 6 to 7 times slower than the fastest thing. Now it's only about 2 to 3 times slower. So so that's pretty good. All right. Any questions on any of the things that look surprising? Yeah.
About in multicore or in for each about the.
So I have an example using for each in just a second. If you want to wait to that, maybe.
The question is, so in multicore or for each,
yeah.
It's more efficient to dissect how many tasks to put for each core instead of, let's say I have 4 cores and I'm going to repeat something 16 times.
Yeah.
So instead of, sometimes a multi-core would switch 4 times for the same core, always changing. So sometimes it's easier or more efficient to reorganize that. So I have a question about parallel apply. Do you also have to do it in parallel apply?
I'm not sure what do you mean by sort of like the reorganizing? Okay. Yeah, so I mean, I haven't dug too deeply into sort of like the nuts and bolts of like sort of the actual individual optimizations. There are probably a lot that you could make. These are sort of like poorly written functions in general, but they're just sort of intended to demonstrate some of like the big concepts, I guess. Yes?
Do you know if there's any way to find out the time exactly that the function spent like doing the scheduling versus the time like actual running time? Because what you said, I mean, like from my perspective, like I wonder, like running this with 2 nodes or whatever you call it instead of 4, would it be more efficient?
So I mean, I guess you could actually sort of, you could have these individual things like output the actual time that they spent, and then sort of, so then you could figure out the time spent actually doing the computation here or something like that. So yeah, I mean, you could put some code together to figure that out. That would be interesting. I'd be interested to see that. Yeah.
Then you know when it's working like that.
Yeah, I mean, ultimately, you just have to be thinking about whether you've got a lot of computation sort of going on in here, in your individual things you're sending out. If you do, then it's more likely to be worth it. So also, let's see, I think I talked about it a little bit here. So yeah, so this is sort of your best case is when the actual numbers you get out of the individual functions, the individual like tasks are very small, but it takes a long time to get that number. Because then you don't have to do a lot of like joining all the data. It's not going to take a lot of time there. So it's sort of like the scheduling type stuff. That's going to be easier. It's also probably, this may be what you're talking about, that it's sort of like faster if you have like 4 jobs as opposed to 16. Is that what you mean? Yeah, that's probably going to be true too.
Then you're replicating the global environment only 4 times and not 16 times.
Well, what I think that the way these things work is, or the way the internals of this work, I was reading something about this yesterday, is that they sort of have a global queue, and when one of your cores or one of your R sessions basically finishes with the job that it's on, it grabs the next one out of the queue. So yeah, if it doesn't have to be going back and looking at the queue more times, it's going to do better. Okay, so like bootstrapping, that's something that you could get a lot of benefit from. Yeah, so here's something to be wary of. Pseudo-random number generation across cores will be correlated. So you need to think about that, and you need to like set your seeds separately across the cores. There are also some like, I don't know the details of all these like PRNGs, but there's some other, there's there seems to be one common one that a lot of people use. I forget what the name of it is.
Treatment for it in multiple.
Yeah, yeah. So a lot of some of what I'll show you in a second will like do some of this stuff automatically in terms of making sure that they won't be correlated. But it's something that you should check on when you're doing this sort of thing to make sure that you're accounting for it. Okay, and then there's some other, we mentioned like for each. There's some other ways to do parallelization. There's snowfall. I don't know, like I was looking at snowfall. It doesn't seem like it's much easier than just using snow. I don't really know. Do parallel. This gives you the for each stuff. So here's the way you could do some parallelism with for each. So you basically just do you write a little for loop type thing, and then so normally if you were writing a for each, you would just do, and then whatever you wanted to do. But you just put it in do par instead. So it's pretty easy if you're used to using like loops and stuff in your code. I don't really use a lot of loops in my code, so I don't know about that. But so what I thought was interesting is that doing it like this actually is fairly significantly slower than doing it with like tapply with the sort of sapply to replicate. So that may be something to keep in mind if if these sorts of things that are probably like honestly marginal improvements are something that you actually care about. And they probably aren't for us, because we can just send it off to the HPC and be done with it. Who cares if it takes 10 hours instead of 5 hours? It's not a big deal. Okay, so as requested, here's some multiprocess JAGs in Stan. So, of course, it is conceptually trivial to parallelize chains in Markov chain Monte Carlo. Yeah, so for JAGs, it's actually really easy. There's a package dclone, which is for data cloning, and it has some nice little helpful functions for you to run chains in parallel. I haven't used it, but it looks very easy. You just use sort of like par JAGs model and par coda samples instead of what you would normally use in JAGs, which is, I think it's all lowercase, right? It's jags.model, isn't that right? I don't know, Pablo, you use this much more than I do. Okay. And so basically the only difference is, oops, let's not go there yet. So basically the only difference is that the first argument is whatever the cluster you want to run it on. So it's super easy. The rest of it's exactly identical to the way you would normally run a model like that. But yeah, read the documentation. It's very simple. The other nice thing, and I checked on this, is the package does take care of making sure that the PRNGs are like sufficiently different seeds so that things aren't correlated, so you won't need to worry about that. You just use the built-in functions, you're done. For Stan, you don't get as much help. You have to do your parallelism in any kind of way you want. You just run the different chains basically manually. Not exactly, but basically manually. And then you get them so that they're in a list, so that each of your model outputs is in one element of the list. And then they provide this function which takes a list and gives you a single stanfit object. So I think that's kind of a funny way to do it, because it would be very simple to just like throw in a function that did this stuff for you, but they just haven't done that. So you would just run something like this. So you're running par sapply, so you're farming out the function that you're going to run to the different clusters, and however many clusters you instantiated it with. So then we just run the function, which is stan as usual. So we've already fit a little model to to compile it or whatever, because stan does everything in C++. So then what you do is you set a common seed for all of them, but then you just vary the chain ID. And when you change the chain ID, it automatically jumps to somewhere else to a different seed so that you don't get any kind of correlation. So that's it. at this point you have the list, so then you would just, you would save this to some variable, you would take that variable, pass it into this function, and you're done. You have a single stand fit object with however many chains you wanted. So it's still pretty easy. Yeah, so there are more examples in the R documentation, so look at that, but it's essentially trivial. Yeah, so I already said that. Okay, let's see, how much time is it? Okay, so we're good. So I'll go through this now too. And then we can probably take a break right before I get into the actual HPC stuff. So, as I said, basically everything you do on the HPC is you're just sort of doing like basic Unix type stuff. So because I sort of feel like most people probably don't know that stuff, I'm going to go through some of this like Unix type stuff that you should probably know in order to do things easily and effectively on the HPC. So yeah, so all the user specific folders and all the like stuff about specific users, I just am going to have my own NetID in there, but obviously you would replace this with your own. I hope that's clear to you. It would not work. You would not have access to mine. So folders are notated in Unix like this, so it's unlike Windows, which has slashes the other way. I never know which is back and which is forward, but this one.
The tail does not work?
It does. Well,
Oh, sorry.
yes, they do. So yeah, so that's how this is your home directory. I think I talk about that more in a second. About like sort of what some of these folders mean. So we navigate between folders with CD. We can create new folders with mkdir. So this would create a folder named folder name in my home directory. To see what's in a directory, use ls-l, which will give you additional information. ls, like list files, is what it means. Emitting a folder argument means list the files in the current folder. This is just sort of dumb stuff. On the HPC, though, there are some specific folders that you should know. So your home directory, you have a limit in the size of this home directory, 5 gigabytes. So, this is pretty big, but you could conceivably use that without too much trouble. So what you want to put in here are things like source code, scripts, and also executables. And if you need to install any extra software, you're supposed to install it in home, which I actually didn't realize was the case. And I did it, and I thought I had done it wrong, but actually this is the correct place to like install extra stuff if you need it.
This is the login server, right?
So your home directory is going to be like shared across them. Yeah, I think so. Pretty sure. Yeah, and the compute nodes have access to it too, I think. Yeah. Then you also have this so-called scratch folder, which is user specific. This is the working directory for running jobs. So you have a 5 terabyte limit per user here. So you have a lot of space to work with. So this is where, if you need to save files in the middle of doing some big job, this is where you should save them. Things to remember: inactive files will be deleted in this file system. So make sure that you're moving things away when you're done with them. So also they will get mad at you if you're only like basically changing the access time without actually like using the files. So don't do that. Don't try and game the system. And there are no backups here. I think there are backups in both home and in the other folder we'll talk about in a second, but there are not backups here. So what you should really be doing is you should be like doing whatever calculations, getting whatever like your sort of output is, then moving that somewhere else that's safer. So then this is the sort of final folder you need to think about, which is the archive. This is for longer term storage. It's backed up. It begins with an allocation of 2 terabytes per user, and faculty sponsors can request more. I think up to, it's either 10 or 50 that you can, I think, just ask for. Beyond that, they force you to pay money. But yeah, I mean, 2 terabytes is a lot. So, well, maybe not if you're storing, you know, all 5 months of Twitter or something, but it's a lot for most of what we do. Okay, now some basic file commands. I already talked about, you know, some like navigation and stuff. So you can move folders. You know, this also functions as like a kind of rename between source and destination very easily. You can copy files and folders. You can remove a file called src, like so. And you can make these recursive by just adding the -r flag to them. So also you can read the man pages because there are a bunch of additional options. And so like what recursive means in this context is, you know, it's going to copy the first folder and then everything in that folder, and then all of the things inside the folders in that folder, and so on. Or copy or delete or whatever. Okay, then what I use to actually put things onto put things onto the cluster, take things off, is rsync, which is a command line utility, which is fantastic. But you can also use like WinSCP is a program, GFTP. I don't know what's good in Mac for doing like, so what it has to be is it has to use this SCP, Secure Connection Protocol, I think, which goes through SSH, which we'll talk about in a second. But there's not like FTP access. So GFTP is poorly named because it does several different protocols. Yeah.
But you need that installed on the HPC machine, right? Because you cannot.
SCP? No, SCP is just built into SSH.
But I tried to open an WinSCP connection from my computer to the HPC.
Did you have the HPC tunnel started up?
The first login, you mean?
Yeah.
Yes.
It should have worked. I mean, it's just, I don't ever use the actual GUIs. I just use rsync, but rsync works fine. And if rsync works fine, SCP definitely should.
From your machine.
Yeah.
Okay.
Yeah. And SCP is definitely installed because it just comes with SSH. So for rsync at least, the basic syntax that you use is like this. I don't remember what all these flags mean. I decided they were important at some point. V is probably for verbose, R is for recursive. I don't remember what A and Z are for. But so source from generally like from your source machine to destination. I'll have an example showing how this works with the server in a little bit. Yeah, and there's some funky things with trailing slashes. So basically, like if you have a source folder here and you have the trailing slash on the end, it's going to transfer everything within that folder. But if you don't have the trailing slash, it's going to transfer the folder and everything in the folder, if you catch the distinction. Yes?
So this works, I mean, what you said, so you need to have this HPC tunnel open, and then you...
I'll talk about that in a minute, yeah. So it's sort of difficult because like talking about the tools, I wasn't entirely sure of the order, but yeah, I'll talk about like how to get the connection to, together and everything in the next section. Yeah, so this is going to need the HPC tunnel active first, and then you can log on to the individual clusters to transfer the files. And so then, yeah, so then you would connect to the cluster that you want to put the files onto. So yeah, like the files are going to be, so I think like, I'm not entirely sure whether, I should check on this. I'm not entirely sure if files are persistent across clusters. I don't think they are. I think you're going to have to put them on each cluster individually. I've always just sort of used the same cluster. So anyway, okay. So then here's sort of the fundamental Unix paradigm which you need to understand in order to do some stuff in the cluster. So Unix is based around the idea of simple programs doing simple things that you can then chain together. So you need to understand how to chain these things together. So most tools, you tell them to do something, and they're just going to send their output to the console that you're working with. But we can redirect that output. So for instance, here's the command. We want to just list the files, and when we list files, we get one line per file just going down with information on each file. So we can list the files in a directory, and then this vertical line pipes the output to the next command. And the next command, it's this word counting utility. So I say word count, and then this flag here means count the number of lines. So what this outputs is just, so the first part lists the files in the directory, then this part sends it to the next command, then the next part counts the lines. So the combined command counts the number of files in a folder. So the way you sort of chain these things together is pretty important for the way you do things. So we don't only have to send things between commands, we can also choose to dump our output to a file. So we do that by using this little greater than. So for example, so we could, if we wanted to dump the list of files in a folder to a file, we could do that with this command, which would list the files and then dump that to a file named out.file in the current directory. And then, so this will overwrite anything that's currently saved in out.file. We may just want to append to the end of the file. And we can do that. So maybe we want to list all the files in a folder, and then we want to have the number of files in a folder at the end. So we could do that with this command. So the same thing we did before, count the number of lines in the file, and then append that number to out.file. Then something else we might want to do is, if commands give us errors, sometimes we would like to have those errors go somewhere special. So we can do that too. So if we want everything going to the same file, we do this with putting an ampersand before greater than. And so then we can append in the same way. So what I've started abbreviating is standard out. This is just the typical output you get on the terminal. Standard error, that's the error messages you get. Just for clarity, and that's what they're actually called. But if we only wanted the error messages, then we could just use 2, which is just the number that corresponds to standard error, and we could dump that to a file, same way. Or we could, if we only wanted out going to a place, we could do that with 1. And so yeah, this is going to be useful to us later because, I mean, you can't look at what your program is doing on the cluster when you're running it. So what you need to have it do is you need to have it write what it's doing somewhere so that if it has some problem that comes up, you can see like any error messages it had, or just sort of like where it was. If you have it, printing out, I'm on file X, I'm on file Y, then you can see exactly which file it was on when it messed up, and so then you can figure out what went wrong. So this is sort of like a core concept that you need to know for what we're doing. Okay.
So what happens like JAG's output if you don't say anything?
So JAG's output would be our output.
Yeah.
So what I would do, so if you have an R script that you're running, I would sync at the beginning and so it would send all of the typical output you would get in your R interactive session. It'll just send that to the file that you specify in sync. So that's sort of the easiest way to get a log of whatever you're doing. Yeah. Okay. So now on to some basic file editing. So you can edit files on the command line very easily with just these command line editors like vim, nano, emacs. Personal preference, but vim is what I use for everything, so I think it's the best. We can edit files via command line using the sort of redirecting we saw before. This is also pretty useful. So just to give an example, so echo just sort of prints the next string to the terminal. this command here is going to take this as a line ut text, and it's just going to send this to out.file. So now we have this file out.file, which just has this text in it without quotation marks. But we can use the stream editor, sed, to do simple search and replace on text using regular expressions. And we can do that. So cat simply prints the output of a file, or prints the contents of a file to the terminal. So we can cat out.file. Then we can pipe that output, which is this string, to sed. And then we can do a search and replace using regular expressions. So this says search, then we search for ot space, and then we want to replace ot space with of space. And then we want to dump that to out.file. So we're replacing out.file, which had this, with out.file, which replaces ot with of. So we now just have this is a line of text. And that fixes our typo. So this is also something that I use a lot on HPC. And of course, all of this kind of stuff can be strung together for all kinds of power and flexibility. You could build the internet on this, and people have, like the people who made the internet. Okay. And in fact, these can be placed in what is called a shell script. So just like in R, when we want to write a list of commands to execute, we can do the same thing with commands on the command line. So, shell scripts. We create a shell script by just creating a plain text file. You can name it anything, but typically use the extension .sh for shell. So the first line, you want to tell it the particular type of command line that you're using. And I use bash, no reason to use anything different. Then each line in the file is a command to execute on the shell. You can make the script executable by running this command. So then you'll just run your script with /scriptname.sh or sh scriptname.sh. It's very easy to pass in command line arguments to these shell scripts. So we can refer to them within the script as $1 for the first argument, so on into however many arguments you have. Variables can be saved in the so that you refer to them in the same sort of way. So you just have a line that says var equals 24. Make sure there aren't spaces that can screw things up. Then you just recall them with the $, var, the same way we refer to the command line argument. So some variables, like this, are global in the sense that they're pre-existing once you start a shell up. So one in particular that we're going to talk about is the path variable. This is called your search path, which, so on the command line, you have access to a number of commands. One thing that you might ask is, how does it know what commands are available? And the way it knows is it looks through all of the folders that are listed in path and sees what the names of those commands are. So the commands that you can access just directly are the executable files that are in folders that are listed in your path. And it's listed in order. So it's going to search through from the first folder to the last folder that are listed in a row in the path thing. So for example, if we've talked about the so for example the sh command. If we wanted to overwrite the sh command with something else, which you should not do, I'm not even sure would really work, but just generally, if you wanted to do that, you would want to add a folder to your path and create a new executable named sh in that folder, and then it's going to use that one instead of the basic sh command. So you can add a new folder to your path using this command. So you do export, which means sort of export it to the whole shell. Path equals whatever the new folder we want, then colon, you divide the folders with the colon, and then, so this, remember, recalls the variable path, so then it's going to list all the other things that had previously been in your path. So now I've added a new folder which contains some binary files well, that's not necessarily binary, but executable files within my home directory that it's going to search for before it searches for anything else on the system. So that can be useful to us and will be useful to us. So here's an example shell script, and then I think we can take a short break. So this is a shell script I use on my personal computer to update the files that are on the HPC. So first line, I set the environment. So this second line is very important, and you should probably have in every single script you write, set-e. What this means is that whenever it encounters an error, it stops executing the rest of the things in the shell script, because it doesn't do that by default. So if it has an error at the top, like saving a variable which might correspond to like a folder, it might throw an error and then go on to the next one, which might be delete everything in that folder. And so suddenly you've just deleted everything in your current directory. So you want to do that. So, well, I don't know that I've done that, but it's something that would be very easy to do. So let's see. So here we have an if statement. So shell scripts are like Turing complete, so you can do whatever you want in them. What do I do here? What it's actually doing is I'm searching whether I currently have a connection open to HPC Tunnel, and if I do not, then it tells me on the terminal that I need to have the SSH tunnel active. So then it tells me what command to run. And then it exits. But then, so this command that I have, I also have it so what I'm actually doing with here, so this is for a different thing I've run on the HPC, which is to do some OCR on some PDFs. So sometimes what I want to do is I just want to replace code files. In that case, I just run this command. Wait, is this right? Yeah. Okay. So, God, I don't totally remember exactly what this is. So, but basically, what I have it do is I have it check to see whether I have PDFs on the end of the command, and if I do, then I also update all this like big list of PDFs that I have saved on my computer. But that takes a while. Sometimes I don't want to do that. Sometimes I just want to update my code files. So in that case, so is this a, yeah, that's a not equals to. Okay, I'm having trouble reading some of this close to the pixels. But so what it does is it checks to see whether I have. So this is $1, the first command line argument to this shell script, checks to see if this is PDFs. If it's not, then I run this command and I exit. And this command excludes all files that end in PDF. And then it updates, so it takes the local folder, which is just called CPP, and it sends everything within that folder. So I have the trailing slash, so it sends everything within that folder to the following location. So what you do, we'll get to, in the next section, we'll talk about like host names and stuff, but we have a host name set for the Bowery cluster. And so what we do is we save the stuff that's in CPP to within the directory OCR files, which is in my home directory. Let's see. And so the nice thing about rsync is it will only update, so it won't like send everything in that folder. It'll only update the things that aren't there or have been changed. And then if I do have PDFs in the command line argument, then I just run the full command, which includes updating the PDFs and sending those as well. So that is an example of a shell script. And yeah, and there are like loops and stuff. It's fully featured. But as you can see, like some of the syntax is a little weird with like if, phi for delineating the size, but it works. Okay, so I think now is, okay, so some extra resources. There's a ton of stuff on shell scripting. Those were some of the main points that I'm going to use today for talking about the HPC. But here are a couple links for various things that you can read more about bash scripting, if you would like. So now we're ready to move on to HPC, so we can take a short break.